Well, I don't know if Scotland has the tradition of Pancake Day, does it? Are we the healthy option, coming here instead of spending the evening eating pancakes? Well, there we are. Language. Simple enough for a child to learn. Too complicated for an adult to learn, really. We can try, but we never achieve the same competence as a child. It's fascinating, really. In discussing origin of language, many people would say that language origin is the 8th major transition in evolution. I want to have a look at this major transition. Rather depressingly, Bickerton comments, the evolution of language is far too complex and vast a concept for anyone to say anything sensible about it. So that's a challenge for me tonight. Why is that? Well, language, there's expertise in many, many disciplines, really. Sociology, anthropology, philosophy, neurobiology, archaeology, biology and linguistics. Well, I'm just going to narrow that down to parts of biology and linguistics because it's far too vast a topic. And also, I'm not really going to consider changes in languages from ancient to modern times. That's another fascinating area. I think we've got enough to cover as it is. So, communication, fascinating. It's amazing what's going on between the ear and the mouth. Fascinates us when we watch toddlers and they're just babbling away, and then suddenly there's a few words, and then suddenly you think, oh, I didn't teach them that. Where did they get that from? And it's amazing how language just blossoms. So what are the main components we have to consider in language? That's the first point. That's the first thing we're going to discuss. The second, I want to look at differences between animal and human communication. And really a shorthand, when I talk about animal communication, probably a lot of the time I'm going to use the word call, and for human communication I will use the word language. And that's just really convention, it's just ease there. So when we've looked at the difference between animal and human language, then I want to consider how the theories that are around match up with the data. Right, this is the bread and butter of some speech and language therapy work. Quite a complicated diagram. We'll go through it a little slowly. This is the model that has been developed out of language-impaired children. Children can have a deficit in any one of these areas, either the boxes or the arrows, and gradually a picture has been built up of all the different processes that are occurring. We start with hearing, and that whole biology of hearing I'm not going to cover today. Then there's the pathway up the auditory nerve towards the brain. We have children that have a deficit in this area and they don't develop language. Everything else functioning okay, but they don't develop language in a normal way because sometimes they hear correctly, sometimes they don't hear correctly. And the pathway in the brain and the representations that are stored are just defective. So that's one of my challenges on Thursday morning. The next stepway, peripheral auditory processing. I think not a lot is known about that area. We pass on to speech, non-speech discrimination. When we listen, we have a marvellous ability to screen out non-speech sounds. There's the sound of the projector there going. We're not really listening to it, it's just gone. So we can do that, we've got that facility. We home in on speech sounds and then we discriminate. When we hear speech sounds, we actually categorise them. There's very many variations in speech sounds, but we categorise as b and p, for example. Well, there's a whole range of sounds between. We don't notice them. We just categorise which sound we've heard, so we know whether it was big or pig that we said. If it's a new sound, so if you're dealing with children under 1, they're learning the sounds of their own language and they're learning to discriminate those sounds. So that's what we mean by phonetic discrimination. Once we've got the hang of the sounds of our language, we would call that phonological recognition. We recognise the sounds of our own language. So moving on from there, this stream of speech sounds that's going up your ear, you're picking up the speech sounds, you're matching it with the representation you have in your brain, and then from that you're moving on to look at the meaning. You're moving into the semantic representation of what I'm saying. You've picked out of this stream of sounds the speech sounds, and then you're picking out the words. Now, what isn't shown in this diagram is that we are also analysing the grammar of what I'm saying. And that's just not shown on the diagram because it's just really rather complicated. But after that, then you understand what's being said. And after you understand what's being said, then you've got the choice of replying. And then you're going to decide what you might say. Then you're going to decide the tenor in which you're going to say it. And then you put together the grammatical framework. And after that, you pick out the words you use. And that's where we need to go back to the semantic representation here. So when we've accessed the key words we need, then we need to go on and access the motor programs to produce those words. The motor program to produce each of the sounds in those words. If the word is new, we might have to access some motor programming. We're also going to access motor planning in order to string the sounds together. We're then going to have to send the signals down the nerve, rapid number of signals to the muscle fibres, and then we speak. Now, there are children that have problems in 1 or 2 or 3 of these areas. That's how we know these exist. So that's just a bit of the pathway that we go through. So let's have a think now as to how animal and human communication differ. What's the difference between it? Firstly, animal calls have a genetic base. There's no option really there. If you're a finch, you have one type of language, one type of call. If you're a blackbird, you have another. Really, it's a genetic base. There is a short learning period. We all know about imprinting in ducks and things, but there's a short learning period. But basically, language is inbuilt genetically. One example is the bee waggle dance. Bees have an amazing dance when they get back to the hive, and they can describe where the food source is, how far away it is, and how rich it is. And that they do that by the speed and the orientation of their dance. They don't learn that, that's inbuilt. Vervet monkeys, they have a small number of sounds, perhaps 10. There's one for an alarm call for snakes, there's an alarm call for leopards, there's an alarm call for eagles. There is a short learning period. The young vervets have to learn that there's no alarm call needed for falling branches, but apart from that, it's very definite calls, very clear, and it's innate really as a genetic basis for them. What is different is that we are able to teach so-called words to animals in captivity. There's been a lot of research done on dolphins. 2 languages have been used, either underwater speakers in their enclosures or a system of hand gestures. And the dolphins have been taught to follow commands. Obviously they can't respond, but they follow commands and they will do it. So words like frisbee, ball, hoop, so you can say to the dolphin, put the ball through the hoop, things like that. They can learn to do that. They're trained with food. Apes, there's been quite a lot of experiments on language learning in apes, and we'll come to that a bit later. But some animals can learn words. However, compared with the way children acquire vocabulary, it's very, very different. About the age of 2, it's like a volcano. Language just develops, it just takes off. We learn words, Chomsky says, much quicker than that can be accounted for by a general learning mechanism. So if you think of a 2 to 3-year-old learning words and then compare with learning to write, that's a slow and arduous process. There's a very big difference. There's an innate component there to learning vocabulary. So calls have a genetic basis. Animal calls, secondly, are automatic. A vervet sees a snake, it's an immediate response. That vervet will make a call, and all the other animals in the troop will disappear off in the right direction to avoid that predator. The same with birds. There's a cat in the garden, that blackbird will make a call, and it's immediate, and the animal really has no choice. That blackbird will make that call. The calls have very specific meanings, usually a small number of meanings, like this is my territory, get off, or perhaps this is the predator, this is the cat, an alarm call to get out of the way. Trained animals have more capacity. Trained apes, highly trained apes, there's one known as Nancey. After several years, it was able to initiate conversation. Most of the time it's just a response. It wants food, so it would point to something on its board to say what it wanted. But on a few occasions, this particular ape commented on things quite out of the blue, which is really quite a human trait. It complained that its mother had bit it, matata bite. So there is some ability to initiate there, but only in trained animals. By contrast with that, humans, we can decide whether we're going to speak. We can decide the way in which we're going to speak. It's not automatic. Thirdly, animal calls are broadcast. They're not directed at anybody in particular, any other animal in particular. A vervet saying there's a snake around, it's just like us when we say to a group of children near a road, car. We're not actually talking to anyone in particular, it's just a general comment. And this is really what animals are doing, whether it's songbirds or the vervet giving the alarm call for the animal. Now the trained animals are slightly different in that they will speak to individual trainers, individual people that are with them. But contrast this with babies. Babies at 8 months develop the skills of shared attention. They get your attention, they get your eye attention, they make faces. You make faces back, and shared communication is off. Something else about human communication, we say it always predicates. What we mean by that is we always are saying something. We're either asserting or denying something on a topic. So for us to say car when there's a car coming is not full communication. But when we say, look, there's a car coming round the corner, we are saying something about that car. That is really communicating. Calls are broadcast, language is directed to individuals. Another difference between animal communication and human communication is the number of calls. Animal calls are usually small, certainly a fixed number. Vervets about 10, chimps up to about 30. That's what they're giving out. Now what can they hear? What can they distinguish? Well, cotton-top tamarins are really quite an interesting set of work has been done with cotton-tops tamarins in that they're given language to listen to, perhaps syllables, perhaps words, perhaps sentences. And if they turn their head, it shows us something different because they're interested enough to turn their head. Once they get fed up, they just turn back, they turn away. So that was the parameter used to show whether they were hearing something different or something that they were familiar with. So they were made to listen to Dutch and Japanese. And first they had the Dutch, and then after a while they got a bit fed up and they turned away. And then the experimenters switched to Japanese, and immediately they turned again because this was different. Now there could be a variety of reasons for this, and so the experimenters wanted to know whether they were distinguishing the sounds of language as we do. So they played it backwards. And interestingly, these cotton tops just showed no difference when they made the switch from Dutch to Japanese. They didn't know the difference. So it looks like cotton tops are actually picking out the acoustic features of language rather as we do. Amazing. There are other animals that do something similar. Chinchillas, macaques are two other examples. In human language, we discriminate, we categorize the sound that come up. And we produce many discrete sounds, but we don't produce the whole array. It's not a continuum of sound as we have a continuum of volume when we speak. This is a very important feature in how we can say so many different things, why language is what is known as discrete infinity. Now sounds, you may think, no, there's not 26 sounds. In English there's about 40 sounds. In some languages, though, I think the highest is something like 150 sounds. But there are even more sounds in total. And we have a certain number of them in our language. But they're not just sounds that we match in our brain. We're not matching the sound B to a feature in the brain. We're actually picking out features about particular speech sounds in about 8 dimensions. So if we talk about the sound B, for example, when we make it, we're using our voice, B, as opposed to P, which doesn't use our voice. Is certain feature about that sound as an explosive quality to it, and it's made at the front of our mouth. So there's some of the features that we are matching with in our brain, but there's 8 features in total. And this, in organising this, there's actually a very complicated structure. And to look at this structure, we're going to take the sentence, the little stars beside the big star. So we go on to look at the structure of that when it comes to speech sounds. And we know this because this is the way we analyse and produce speech sounds. And so this is a way to look at them. And this is present in all languages. And the central feature of speech sounds is the nucleus. Okay, so let's start on this line. You see those N features, those N letters along there. They each correspond to the nucleus of the word. So if you look down there, there will be a vowel. This is written in phonetic script here, the little stars beside the big star. But along these words, you will see a number of nuclei here. Here's another one, big. The centre part of that word is the vowel. And clustered around it is what we call the coda and the onset. And we store words and retrieve words by the onset. Typical child's game, give me 10 things beginning with the sound P, I Spy games. We can also rhyme. Children love to make up nonsense rhymes. If I asked you to give me half a dozen words that rhymed with big, that would be no problem for any one of you. So we store words like this in this hierarchical structure. Another feature of the structure is the prosodic structure. This is really the music of language. When we talk, we don't just talk in a very stilted voice like this. It would be very difficult for you to understand what I was saying if I did that. But we have this structure of rhythm and volume here, denoted by the X's, that show us how language is split up in our minds, and this helps us to understand language features. Another feature about language is that what we say is split up, but not by words. We do not speak in individual words. Sounds dreadful, doesn't it? But we link words together. So, for example, coming down to the bottom, we see here the little. Now that's run together as one word, the little, and then there's a break. Stars beside the big star. Now that D there is actually shared between beside and the. It's coming in both words, so we're running words together. So this structure we see here is totally unrelated to the meaning, and yet it's a very important part of us absorbing and understanding what we say. Okay, we'll go back to comparing human-animal communications again here. The next thing we need to consider is that when we speak, our words are symbolic. What we're talking about doesn't have to be present when we're talking. It's not meaningless, but if an animal is giving an alarm call, and the reason for that alarm call isn't present, then that call is meaningless or misleading. So a vervet will produce an alarm call for a snake. It will continue to produce that alarm call after the danger has gone. It's valueless. In fact, it's totally misleading, but that animal continues to do it. But when we talk, the way we structure our language, it is meaningful. We can talk about imaginary things, that's still meaningful. The question arises is, when does an animal call become meaningful? Does it ever become meaningful? There's a lot of discussion about this, and one possible feature is if an animal can remember something for a certain period of time after that object is out of the way. Maybe that is symbolic, as we call it. Are animals able to store words? Well, some monkeys can remember for perhaps 5 minutes. Dogs can certainly remember things for a long period of time. So there is some symbolic, something approaching symbolism in animals, but we do find it in trained animals. Of course, trained by human beings and often trained with food rewards. Dolphins can remember probably up to 29 words. So if the trainers say, put the ball through the hoop, the animal can remember that for about 30 seconds and then do it. Interestingly, some of the trained apes can talk about absent objects. Kanzi has been known to plan the day's activity using his symbol board before going out, deciding which area of the forest to go to. So yes, there is something approaching symbolism, but there's lots of discussion about it, and I think opinion would be divided. Certainly there's a big difference between human language symbolism and the way animals use calls. Human words can be linked to any concept. Take, for example, the word tree. We can relate that to a tree in the garden. We can relate that to a family tree. We have no problem manipulating words in that way. That is symbolism. When we get up to adult age, we've probably got stored 50, 60,000 words. We can't just store them and retrieve them without some sort of system. And this is what I want to go on to look at again. We store words by a whole variety of functions, and we can retrieve them. Now, this is an attempt to show the type of network that there is conceptually in our brains to retrieve words. Okay, that's just the same. I'll just leave that up a moment because the last slide was perhaps a bit difficult to read with the background. Let's go back to that sentence again. The little star is beside the big star. What concepts have we got to retrieve to say that sentence? We've got to retrieve star. We've got to retrieve the property, big or small. We've got to retrieve the verb, the doing word, the present existence of that object is. We've got to retrieve the place, the locative relationship, the beside. And then we've got to put all that together. Well, to retrieve that, we've got to access our vocabulary store. And this is multi-dimensional, it's also hierarchical. We can say, give me 10 animals, that's no problem. We can say, give me 15 jungle animals, that's no problem. We store words hierarchically in our brain. We also store not only by group, we store by function. So I could say, give me things that shine. A star would be one of them. Give me things in the sky. A star will be another one. Give me things related to festivals. You may come up with star again. So we can retrieve words in this way. Also, there are words we can't quite retrieve. Have you ever had that feeling? You know the word, you know how many syllables it is, and you think it starts with a s, but you're not quite sure what it is. Well, this shows you something of what's going on in our brains when we're trying to retrieve words. When we retrieve words, we can also do it, unsurprisingly, by first sound, by syllable number. That's referring back to the diagram I showed about speech sound structures. We can also retrieve through action words. And in our store of words, there's also quite a bit of grammar. Grammar and word meaning overlap. When we work with stroke patients who have problems retrieving words, we would do therapy that involves strengthening these pathways, strengthening their ability to retrieve words by group or by function or by location. And this enables people to access words and communicate again. Okay, let's return to our comparison of human and animal communication. Calls are a hollow phrase. That's a lovely bit of jargon. What it means is that the whole call has one meaning. So a vervet alarm call, the whole call means a snake or a cheetah or an eagle. You can't break that call down in any way. You can't reorder. You may be able to reorder it. Maybe some animals do reorder how the call is presented, but it still has one meaning. The one call that can be broken down, it's not a call, the honeybee dance, we can break that down into two features. We can break that down into speed of dance and orientation, but we need to put it together to give the one message, and that is, where is the food located? Human language, by comparison, is composed of discrete parts. Human language is much more, well, it's like Lego, really. We take individual bits and we can combine them in an infinite number of ways to create complex messages. Some experiments on chimps, helping them to try and learn to communicate. There's been a lot of controversy about this work, and there was one chimp called Nim Chimpsky. Well, that's a takeoff of the linguist Noam Chomsky, and a lot of things were claimed for Nim Chimpsky. But when the work was looked at again, and the video clips were analysed again, what they found was that much of what was done was mere delayed imitation. But more recent work has shown that chimps can do more than that. They can initiate. And certainly the dolphins can understand combinations of words. So here we're getting to something more complex, not just single words, but combinations of words. I want to talk just a bit about Nancey. He's probably the most recently trained chimp. He's a bonobo, a pygmy chimp. And the work was probably of the best quality because mistakes had been made, and they were careful that what he developed wasn't purely a response to being given food, and it wasn't purely imitation. Nancey's probably about 29 now, and first his mother was being trained to use language, and Nancey as a baby actually picked it up much better. But still, thousands of hours of training. This wasn't do this and we give you food. It wasn't that sort of direct response. But Nancey was allowed to wander freely in a reserve with a number of human trainers who would interact with him and hide food, and then they'd have to go looking for it. So it was a more relaxed regime. After about 3 or 4 years of working with Nancey every day, he understood single words. Later, 2 words together. So you could say, put the melon in the fridge, and he would do that. Or throw the ball in the water, and he would do that. Interestingly, you can't throw the water in the ball, and you can't put the fridge in the melon. But later on, he was able to understand reversible sentences. So that would be something like pour the lemonade into the orange, where you could either pour the lemonade into the orange or the orange into the lemonade. So at that point, he appeared to be understanding word order, which is a very important first step, really, in grammar understanding. But when it comes to 3 key words, put the grapes in the fridge, it could be put, or it could be take. It could be the grapes, or it could be orange. It could be the fridge, or it could be the box. So Nancey has to understand put and grapes and fridge. That's where things began to break down. The score was about 50%, 12 out of 21. Now, when I'm working with language-impaired children, if they score 12 out of 21, I will say they have not got that concept. They need a lot more work there. So my view of Nancey is that maybe he can analyse and understand sentences with 2 keywords in, but any further than that he's not achieved. He will sign keywords, and at the bottom you can see a diagram of his lexigram they used to use to point, to say what he wanted or what was to be done. He would sign, but he wouldn't order. So if it was put the grapes in the fridge, you might get put fridge grapes, put grapes fridge, fridge grapes put, and all such combinations. So you would get misunderstandings there. So put the lemonade in the Coke. You might get the lemonade in the Coke, or you might get the Coke in the lemonade. So there's not the understanding there. He's not consistent in his understanding of grammar. Okay, let's move on. So we've really talked about rule-based sequences with Nancey and the Coke and the lemonade. And another area of research has been to see how far animals do understand rule-based sequences. And there has been quite a bit of positive evidence. For example, macaques able to memorize sequences in laboratory work, and forest guardians are sensitive to serial order of call, and tamarins too can identify rule-based sequences. So if you give tamarins, say you give them a sequence of syllables, like A, B, A, B, A, B, A, B, they will get bored after a while and they just won't listen. But if you give them A, if you go on for long enough, they get bored. But when you start saying B, 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 then they will turn back. They can cope with A, B, but when they have a long series, if the rule was, say, 5 A's and then 5 B's, 5 A's and 5 B's, that is really a long-distance relationship, and they cannot cope with that. They can only cope with very short-distance systems. And that's important because in human language we have very long-distance relationships. Let's have a look at this sentence here. The cat killed the mouse. Okay, but that's not what's on the screen. We've got a whole series of subroutines here. The cat that killed, the rat that ate, the malt that lay in the house that Jack built. So what's happening in the full sentence, the cat ate the mouse, let's say, is that you get the cat and then you're enlarging on the cat. Which cat? The cat that killed the rat. Which one? The cat that killed the rat that ate the malt. And so you can see there's a whole series of subroutines. Then we return to the top and move on to the next part of the sentence, whatever it is. So we need a stack of pointers to keep track of where we are. This is quite complex. Anybody involved in computer programming will understand that. In language, grammar, we have 4 layers of regulation in our grammar. This is the first one, that language is ordered into these constituents, and we saw that on the last slide. And here we see it again with our other sentence, the little star is beside the big star. The star can be enlarged to the little star, that can be enlarged to the little star with 5 points, and so on and so on and so on. So they're each structured within an envelope. And then the next envelope, that's the verb, is, but we can enlarge on that. We can change from is to might be. And then the next one, beside the little star, we can enlarge on that. But it is carefully structured. And there's a careful subroutine there. And then we return and move on to the next constituent. And syntax, which is grammar, it'll do as a synonym there. This regulates how words are combined into sentences. The next layer is that our words or phrases, such as the little star, are ordered to make sentences. So in English, we have the subject, we have the verb, and then we have the object. The little star is beside the little star, that beside the big star. That is the end of the sentence, not the object. And so in English, we always have the subject and then the verb and then the object. Not in many languages. Many languages would have the verb at the end. But there is a definite ordering in all human languages, and that is the rule at this level that there will be ordering. Some languages don't have much ordering, but we can see that another feature later is more important. The third layer is that in grammar we have agreement for number, person, grammatical gender, if you have that in the language. So we always have our verbs agreeing. We use is or are appropriately, singular plurals, and our grammar is constrained so that the meaning is clear. The fourth layer is case marking. We don't have much of that in English. Any of you that learn Latin will understand about case marking. We still have it in our prepositions. We change our prepositions, he, him, his, she, her, hers. We change our preposition depending on what role it plays in that sentence. And all these four layers are important in giving the meaning of our sentence. There are a load of other features we can talk about. Tense markers, questions, command formats, restrictive clauses. We've come to the church tonight because there's a lecture. It's a restrictive clause. There are long distance dependencies. If the weather is cold, then I need to put my coat on. And all these things need to be programmed in. They need to be understood. So, language encodes long distance dependencies. Here are just one or two examples here. Either the girl eats the ice cream or the girl eats a nice lolly. This is another one. The daddy one is typical sort of thing you find in a linguistics textbook. Marvellous, priceless really. Daddy, what did you bring that book that I didn't want to be read to? And by then he's committed himself to a whole load of grammar widgets, really, to be read to, out of, up for. And that shows you the complexity of grammatical structure. Another thing that we use is a merge command. Take that top sentence, either the girl eats the ice cream or a nice lolly. We didn't have a subject to that second part, but we didn't need one because we refer back to the first one. Okay, so this is a bit of a summary of grammatical hierarchical structure. If I can get the pointer working again, we'll have a look at that. Okay, here is our unit of constituent of the sentence here, the little star. Okay, so we order this. We can make it bigger, we can make it smaller, the star, or we could have the little star that I cut out of a piece of paper. That's all this constituent here. The next one, the next constituent, okay, is the verb here. In fact, it's is. Well, is has something else attached to it we'll come back to in a minute. And this is the third constituent, beside the big star here. But within that constituent, that's the beside, the big star here is a constituent within a constituent. So that's that first level. The second level is the sentence level. So we have, over here we have a subject, over here we have the verb, and over here we have the preposition phrase, beside the big star. So these are three constituents, and that's how it is in English. We would never say the little star, the big star, the little star beside the big star is. We just don't say that. Okay, the next structure here is the verb agreement. The little star is. There's only one little star, so we're using is. There's no agreement of nouns and function in the sentence, because in this sentence there is none. There's no he, she, any pronouns, so I can't demonstrate that here. But that shows you the complex structure of our grammar. We're moving on to the last difference between human and language communication, and really I'm not going to dwell on this very long, except to say that the structure of the animal head and neck is complicated and adequate for their communication. The structure of the human head and neck is more complicated because we have very fine movements to make. So if you look at that cross section of the head on the right hand side and look at the numbers, when we make certain speech sounds, we are moving the bottom part of our mouth towards the top part of the mouth and making very accurate contact. So if you want to make the sound B, you join the two number 2s. If you want to make the sound T, you will take 16 and you will place it beside number 4, if you can follow that. And if you want to make the sound K, you will take 15, which is halfway along your tongue, and you will make it touch point 7. And these are very precise, and we repeat them very precisely and very accurately. So we have more muscles than animals, although chimps could probably make a lot of the sounds that we make, but it would appear that neurologically they are unable to make the same distinctions, because our neural system is much more complicated. There's a lot more myelination that provides for fine and rapid synchronized movements. And there is a condition known as auditory neuropathy, where the auditory nerve is affected, so the signals are not getting up into the brain, and often the children don't develop the same quality of speech and language. Classically, it's said that language production is located in Broca's region in the front of the brain, and understanding language in Wernicke's region towards the back. With recent scanning techniques, we now find that it's much more diffuse, but there is not so much diffuse as networks moving between the front cortical area and subcortical components, and also the cerebellum, which is located at the back of our brain, that's known to be involved in synchronization. So it's a very complicated system there, providing for accuracy and repeatability of movements. So let's summarize that and look at animal skills, and then look at the gap between animal skills and human skills in language. We see compositionality in the bee dance, just 2 dimensions though, but very superbly communicating to the beehive where food is. Compositionality is really not found in any other animal, although there can be features that can be broken up. Zebra finches are thought to have some sort of structure, but recombine it and it doesn't give a different message. There are certainly skills of learning in the animal world. Birds learning sounds and their song in very early stages. Vervets learning what they should use which call for. But by and large, the vervet language is innate. There's not much learning there. Trained animals, it's a different story. There certainly is ability to learn, but it's a slow process needing lots of repetition. Memory is an important feature of language. There is ability there to learn. Diana monkeys can remember for up to about 5 minutes. So if another animal makes a call to say there's an eagle, a Diana monkey will take the appropriate action, and then within 5 minutes, if that call is given again, the appropriate action is not as marked because they know they've taken action. So that's very interesting. They can remember over 5 minutes, and their behaviour is seen to be slightly altered. Imitation is very important in language. Children imitate. Babies, you make a face to a baby, that baby will imitate that face just for the sake of doing it. We all know about parrots imitating. Maybe we're not so familiar with whales. Elephants, an African elephant can imitate an Asian elephant song, an Asian elephant call, and can also imitate the sound of a lorry. Fascinating. Dolphins, they can imitate too. Now, categorical perception, this is what I was describing as the ability to categorize sounds. So up here in Edinburgh, you will make vowels slightly different, some consonants slightly different from me, and yet I will be able to categorize your r as r, which is how I would say it. I can do that, and I can understand what is being said, because we have that categorization. And we've talked about tamarins categorizing and able to listen to Dutch and Japanese and see that there's a difference. So that's an important skill. Chimps, good non-verbal skills, lots of body language about chimps, lots of facial expression, but they are very poor at imitating. So you might expect chimps within an evolutionary framework, you'd expect chimps to be much nearer in evolutionary terms to humans, and yet they don't have that skill of imitation. Understanding and using combinations of words, we only find that in trained animals and after considerable training. So let's see what the gap is. Animal calls are genetically programmed. You never get variation, whereas humans, we can learn as a child, we could learn any language of the world. There's nothing in our genes that says we are learning English. We could learn any language, and of course we can. As a child, we can learn 2 or 3 or 4 languages with no problem. So it's not, the words of language are not genetically programmed, but there are things within us that's genetically programmed that enable us to learn language. Animals, the whole call is a unit of meaning. Can't be broken down and recombined to make something different, whereas human language, the whole thing can be broken down into units of meaning and recombined to make a totally different meaning. Only human language predicates. It's only humans that will say something, will assert or deny something about a certain object. The animal call is just broadcast and just saying there is something, there is danger, there is a snake or a leopard or something like that. The meaning of that just doesn't exist if that snake or leopard isn't there. So totally different from symbolic words. Language, as we have seen, human language consists of hierarchical structures. We've seen that in speech sounds, we see that in words, and we see that in grammar. And within grammar we have other functions like recursion and embedding and merging functions. So considerable gap there. So from that evidence, do we see evidence that fits with biological evolution? And I would say no, no way. There's no evidence of gradual evolution from primitive animals towards primates towards humans. Now, I know it will be argued that in evolutionary pathway, humans are not evolving from apes or chimps as we see them today. You're actually looking at the last common ancestor. The problem with that is there's no evidence to argue for or against anything. So the best we can do is look at what animals have now and compare it with what humans have now. If we're going to hold to an evolutionary origin of language, we've got to explain where grammar came from, where that hierarchy came from. We've got to explain the origin of symbolism. We've got to explain the many layers of complexity that there is in language. We've got to explain the integration of those complex systems. And if we're thinking about language evolving gradually, so first there may be a few half-understood words, we've got to balance the possibility of success in communicating with total failure. How many times have you watched somebody try to communicate with somebody with another language that only speaks Pidgin English, for example? We very soon get frustrated and wander off or get embarrassed and give up. I wonder how many animals, perhaps in an evolutionary perspective, that are developing language, I wonder how many of them would think it much more profitable to go away and find breakfast than try and understand what another developing human is trying to say. And also the cost of failure. We can't cope with 50% success in communication. We've got to have 100% success, because 50% success is total misunderstanding. I once sent a text message in the early days of mobile phones when I wasn't very competent, and I immediately got a reply, "You are racist, I'm having nothing more to do with you." And what had I said? I said, "Would you like some help in this matter?" And totally misunderstood. Somebody whose third language was English. Total breakdown in communication for probably 2 months. So failure is devastating. Another thing that has got to be explained in evolutionary thinking is, why is language vastly more powerful than can be explained by reproductive advantage? It's okay to suggest that, say, Darwin's finch on the Galapagos, a Darwin's finch with perhaps a slightly larger beak, survives in drought conditions because it can crack open larger seeds. That's fine. But how can you explain the complexities of language and the fine differences we can put on things, the way we can talk in very many different styles? There's no way that can be explained in evolutionary terms. So, what alternatives are there? Well, there is an alternative, cultural evolution, that is being looked at. Now, this has developed from computer programming, pattern matching in the 1970s. And the idea is that it's explaining the origin of rule-based systems. So if you think of the grammar rules, this is an attempt to explain the origin of rules. And what these programmers are saying is that rule-based systems perhaps can emerge without genetic evolution. They can emerge by the interaction of learning, culture, and biological evolution. At first it was used to look at how languages change, and that's fascinating, looking at learning. But now it's been extended to look at the origin of language from nothing. And this is where I would take issues with a few things. This is just a diagram to demonstrate the thinking. The green oval represents genetic evolution, the selection and mutation of genes and passing on through generations. Now, each generation has to teach the children. So there's a bottleneck there, really, because the only language that's going to be passed on is teachable language. And then children, as they grow into adults, they will communicate, they will try to develop communication, and so successful communication between adults, that sort of language, if it's developed, that is the language that's more likely to be passed on to the next generation. So not only are they suggesting that language can evolve genetically, but also that language can evolve by communication between people as adults. So, and it's that part that they're trying to model. So, in the computer modelling, they initialise it by providing Model 1 with learning and production algorithms, and also an initial hypothesis. And then they give them some codes, some signals, which will consist of letters of the alphabet, so A, B, 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 whatever it is. And also, the task to be done is to relate that to some sort of meaning space. So they're attempting to simulate language in terms of a signal and a meaning space. And as Model 1 transmits to Model 2, Model 2 develops some sort of hypothesis as to what is the relationship between the signal and the meaning space. After a while, Model 1 departs, Model 2 then starts to transmit to Model 3. And so the iterations go on over many generations. And what these people are saying is that over time, rule-based language emerges, but only if there's a bottleneck. Now, if we have a language where every sample of that language is spoken, then we don't need to break down into rules. We can match one thing that is said with one meaning. But in this case, there's a very narrow bottleneck in that there's only a sample given, and the Model 2 has to build up some sort of rule system. And what the modelers are saying is that cultural transmission is a bottleneck, because we don't hear every sentence of our language. We only get a fraction, and so we've got to build up some sort of rule system. And this means there's a bottleneck, and therefore rule-based language will emerge. A few issues I have with this conclusion is that they're only working at the level of speech sounds. There's no real meaning in there. And also the size of their meaning space is just a small vector, whereas in human language you're dealing with infinity. Well, that's fine. Modelling always deals with simplified systems, but I'm taking issue with how they are drawing their conclusions and how they're generalising it to the origin of language per se, because they've used conditions that don't relate to the development of human language. For a start, these models have direct access to each other's meaning. They're only trying to link the signals to the meaning. Well, if language is developing from nothing, the two original hominids will not have access to each other's meaning. Also, these models, they have no choice. They've got to transmit. They are motivated to transmit, whereas hominids without language, what motivation is there if there's no meaning? Also, it's based on statistical association. So Model 1 transmitting to Model 2, Model 2 may have a rule that says, well, I'm 20% sure these letters relate to these meanings. Well, if we had a language like that, we wouldn't transmit it, because if we're only 20% sure of something, we're going to forget it. So partial development is not something we would pass on. The other feature that is in the models is the suggestion that partially developed language, fuzzy meaning, means that mistakes can be made. And this is a parallel with genetic evolution, in that mistakes can be used to allow innovation so that we can get more complicated language structure. Well, stable structures, rules, they certainly can emerge in the modelling, but only because the conditions they are given are very unlike those where language would develop. In human language, no one's going to figure out meaning until there's a stable structure. You can't get a stable structure until there's useful meaning. We'll pass on from cultural evolution to the third option, and I would say what we've seen tonight clearly shows positive sign of intelligence. We have many unique features not found in the animal world. There is no continuity. Animals have some very highly developed features in some areas, but there's no continuity with animal calls. There I'm listing symbolism, predicate argument structure, long distance dependencies. These are all features we only find in human language. We don't just find one set of hierarchy, we've got several. We've got the hierarchy of speech sound structures, we've got the hierarchy of words, structures, storage and retrieval, and we've got the hierarchy of grammar. Also, you've got to think about the interface between these systems. Now, evolution does not predict hierarchical systems. Hierarchical systems cannot develop by the simple processes of biological evolution, of mutation, loss, replacement. These are things that occur step by step, additional features. So totally contradictory to evolutionary ideas. And if it's suggested that maybe parts of human languages were taken and co-opted, well, the question I would throw back is, where are these features that have been co-opted? So, to conclude, really, I would suggest there are positive signs of intelligence with these unique features, the hierarchical system, the fact that evolution does not predict hierarchical structures. Cultural evolution adds nothing at the moment because their starting conditions are so different. And my understanding is that the best explanation would be by intelligent design. And I think that's probably a good point at which to throw it open for question and discussion. Either